Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is flip equivalent binary trees. Okay, so you will be given for a binary, basically for a binary tree, we can define a flip operation as follows. Choose any node and swap the left and right child subtrees. Okay, and a binary tree X is flip equivalent of binary tree Y if and only if we can make x equal to y after some number of flip operations. Okay, so basically you have to interchange whatever is on the left hand side and right hand side, okay, in a flip operation. And two binary trees are said to be flip equivalent if uh, after some number of flip operations you can make them look alike. Okay, and given the root of two binary trees, root 1 and root 2, you have to return true if they are flip equivalent or false otherwise. Okay, so basically for the flip operation, so for the flip operations, if let's say there is a coin, okay, and right now it is showing head, okay, and on bottom side it is tails, okay, and if you flip this coin even number of times, it will still be showing head, even or zero number of times. Okay, so zero or even, then you will still be getting head. Okay, the state will only be changing when you flip it odd number of times. Okay, so either, see, let's say there are two flip equivalent trees. Okay, let's say this is 1 2 3, and let's take another tree which is flip equivalent of it. Okay, so see, although right now these two are not equal, but the yellow one can be made equal to the green one by doing a single flip operation or doing a flip operation odd number of times. Okay, if you do it even number of times, you will end up having this only. Okay, in order to ha have this green one, you have to do it odd number of times. Okay, so there will be two kind of scenarios. Okay, so the very first kind of scenario is you may have flipped even number of times or zero, or you may have flipped odd number of times. So in case of even number of times, you would be having them in the same order. So this can be considered as a result of even number of time flips. Okay, so if you flip this one even number of times, no matter how many times you flip, if the time number of times are even or zero, then you would be getting this. Okay, so two kind of scenarios can be there. Either if let's say you are at a particular node, let's say you are here only. Okay, so the very first thing that two trees must be having is the current node that we are at should be same. Okay, if we are at these two particular nodes, these two should be same. Okay, or if you are comparing this one also, so this one also needs to be same. Okay, the next situation is that either current left child and right child will current left child and the right child of basically left child of one tree, let's consider this t1. Okay, let's consider this whole as t2. Okay, so either t1's left child will be equal to t2's right child. Okay, this can be a scenario. So here left child of t1 is 2, right child of t2, uh, basically the current node if we are taking is uh, 2. Okay, so these two are matching. And there can also be a scenario if left child of current node, let's say this is t1, okay, is equal to the left child of the other tree, let's say this is T3. Okay, so left child of T1 is equal to left child of T3. Okay, so either of these two situations will be happening, but it must be make sure that the current node at which we are at should be same. Okay, and let's have a look at the constraints before thinking of an approach. So according to the constraints, the number of nodes will be of order 100, and entries or the node values in this particular tree will be unique. Okay, so we can compare nodes by checking their values. Okay, so these values of the current node should always be same. And what about their siblings? Either their left subtrees should be equal uh, to the right subtrees of the another one, or their left subtrees should be equal to the left subtree of the another one. Okay, depending upon the kind of scenarios which might have happened. If you are flipping a tree zero or even number of times, then it would result into the same tree structure, and if it is odd number of times, then it will be a chain structure. Okay, so so once you are at a particular node, so let me clear things up. Let's say you are here, okay, and in the green tree you are also here. Okay, so we are parallelly moving, let's say kind of two pointers on both of different trees, and right now they are having values like this. Okay, so then you would be doing the same recursive thing of checking the children's and everything uh, for this subtree. Okay, so this will again be a sub problem. Okay, so this will be a sub problem. So you see, we are kind of solving this problem recursively. Okay, once we are at a particular node, we are considering two scenarios. Either its left child could be equal to the left child of the corresponding node in the second tree. Okay, or its left child would be equal to the right child of the corresponding node in the second tree. Okay, so we will be considering all those scenarios and we will be solving the problem recursively. Okay, now we will be seeing that in implementation. Okay, so let me copy the code and bring it to the board. So this is the code. It's a quite a short implementation. So what we would be doing here is, see, these one are the base cases. We'll be discussing them in a bit, but for now let's just focus upon these two. Okay, so you were given to complete this function and you were given input as the roots of the two trees, let's say T1 and T2. Okay, so what you would be doing is, the very first thing that you would be checking is the current node that we are at. So this is the current node kind of. Okay, the values of these two nodes should always be same. If they are not same, then you would be returning false, saying that the two nodes are not flip equivalent. Okay, okay, and if they are same, then you would be proceeding further and you would be checking things recursively. Okay, so you would be doing recursive check for the left and right subtrees. Okay, and there will be two kind of scenarios. The very first scenario is I have named it same comparison. So what would be happening in the same comparison is, uh, you would be comparing the left child of the first tree with the left child of the second tree. It will be this kind of situation will happen if you have flipped the tree even or zero number of times. Okay, so and similarly you would be comparing the right child of the first tree with the right child of the second tree. Okay, and then if uh, this kind of situation is not there, then there must be this situation where left child of the current tree will be equal to the right child of the second tree. Okay, so as you can see here, left child of the current node, okay, is equal to the right child of the current node in the other tree. Okay, so this kind of situation will be arising if you are doing the flips odd number of times. Okay, so in that case you will be comparing the opposite directions. So right child of the root 1 and of the first current node of the first tree, and left child of the current node of the second tree. Okay, and either or one of these conditions should be returning true, only then you would be considering that okay, at this particular step of the recursion we have passed the flip test, and we will then again keep on doing these things recursively, and you will eventually hit a base case. Okay, uh, there might be a situation where the root 1 and root 2 pointers are currently pointing to null nodes, both of them. So in that kind of situation you would be returning true. Okay, and if either one of them is pointing to null and the other one is not pointing to null, then in those kind of scenarios you would be returning false. Okay, so these are the base cases for the recursion, and this is how you would be solving it. So as far as time and space complexities are concerned for this particular one, the time complexity wise, if there are, let's say, n number of nodes in tree 1, okay, and there are m number of nodes in tree 2, so the whole time complexity will be order of minimum of n and m. Okay, and the space complexity will be basically how that will be only be because of the recursion call stack. Okay, so that would be the depth of the tree, minimum depth of these two. So order of minimum of, let's say, depth of this particular tree is d1 and depth of this particular tree is d2. Okay, or height you can say. So minimum of d1 and d2. Okay, and if the tree is a skewed tree, it can be up to order of n, and this can be up to order of m. Okay, so these will be the complexities, and this is the approach. So we would just be doing a recursive thing. The only thing that you have to figure out in had to figure out in this particular one was that how the flip logic will be applied here. If you flip something even number of times, and if let's say a coin is flipped even number of times, and right now before the flip it is having head on its top, so again it would be resulting into the same condition, and if it is flipped odd number of times only, then it would be changing. Okay, because see, if you do a single flip, then it would be resulting into tails, and if you flip it once more, then it would result into head. So see, the second or the second flip that you are doing is nullifying your previous flip. Okay, so that's the whole logic, and rest everything will be taken care of by the recursion itself. Okay, and these are the complexities. If you are still having any kind of doubts or any queries in general, then you can ask them in the comment section, and I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Keep solving more and more problems, and I will be seeing you in the next video. Thank you for watching.